If you were to replace our sun right now with a black hole of the exact same mass, the Earth wouldn't get sucked in. We would simply continue orbiting a completely dark, silent void. We'd freeze, but our planetary trajectory would stay exactly the same. A black hole is a concentration of matter packed into an incredibly dense volume, warping the fabric of space-time into a steep gravitational well. Most form when massive stars, weighing at least 20 times more than our sun, exhaust their internal nuclear fuel. Without the outward pressure of fusion to hold the star up, its core collapses inward under the crush of its own immense gravity. Long before we had telescopes powerful enough to spot them, the mathematics of Albert Einstein's general theory of relativity predicted that extreme gravity could distort space to this breaking point. These objects are the natural endpoints of stellar evolution, remnants that push our understanding of physics to its breaking point. This chart maps the massive scale of black holes, showing that they come in wildly different sizes. The spectrum starts with theoretical, microscopic primordial black holes, born right after the Big Bang, moves up to the stellar mass corpses we just talked about, passes through rare intermediate sizes, and finally reaches the supermassive giants. Those supermassive giants weigh millions to billions of times more than our sun. Almost every large galaxy, including our own Milky Way, relies on one of these massive anchors at its center, holding the entire galactic core together. Because their gravity traps light, they are totally invisible in isolation, but we can detect them when they collide. A merger sends ripples in spacetime, called gravitational waves, washing across the universe to Earth, where miles-long instruments like the LIGO detectors catch the signal. We can also spot them by looking at what they eat. When a black hole pulls in surrounding gas and dust, that material forms a glowing accretion disk, heating up to millions of degrees as it rapidly orbits the dark center. By tracking the polarized light from these superheated disks, the Event Horizon Telescope collaboration mapped the twisting magnetic fields right at the edge of the abyss, capturing our first direct images of the black holes in M87 and our own Sagittarius A star. We can calculate their mass, track their collisions, and photograph their borders. These are real, measurable objects dictating the structure of the cosmos, which means we can map out exactly what happens if you get too close. This diagram outlines the boundary separating the outside universe from the inside of a black hole, the event horizon. Here, escape velocity exceeds the speed of light. There's no physical surface, it's strictly a mathematical threshold. Once crossed, all possible paths through spacetime point straight down toward the center. If you stayed at a safe distance and watched a friend fall toward that boundary, the physics would look incredibly strange. As they approach the black hole, intense gravity causes time to slow down from your perspective. You would see their fall appear to decelerate. Their image would turn redder and dimmer as the light loses energy, until they seem to freeze completely at the edge, slowly fading into nothing. They are gone, but you never actually see them cross. At the boundary of a black hole, space and time detach entirely from the standard flow of the observable universe. Now, switch to your friend's perspective. For them, time passes normally. Whether they actually survive the trip across the boundary depends entirely on the black hole's mass. If they are falling into a small, stellar mass black hole, gravity pulls much harder on their feet than on their head. This massive difference in acceleration stretches their body out vertically, while simultaneously crushing it horizontally. Astrophysicists call this process spaghettification. It ensures any object is ripped apart atom by atom thousands of miles before reaching the event horizon. But if they fall into a supermassive black hole, the distance from the center to the event horizon is so vast that the gravitational pull on their head and feet is virtually identical. They cross the threshold unharmed, unaware they even passed the point of no return. In fact, the largest, most massive black holes in the universe offer the only survivable path across the ultimate boundary. Everything that enters is dragged inevitably toward the core, the singularity. General relativity predicts this is a single point where density becomes infinite, and the known classical laws of physics simply stop functioning. While some equations suggest the interior of a spinning black hole could hide a wormhole leading to other points in spacetime, the intense forces and instability make surviving such a trip highly improbable. For decades, physicists assumed matter trapped inside was stuck there forever. But Stephen Hawking proved mathematically that black holes are not perfectly black, and they don't last for eternity. Right on the edge of the event horizon, quantum mechanics allows pairs of virtual particles to constantly pop into existence. Occasionally, one particle falls into the black hole, while its partner escapes outward into space. This process is known as Hawking radiation. Because the escaping particle carries away a tiny fraction of energy, the black hole steadily loses mass. Given enough time, trillions of years into the deep future, it will entirely evaporate. Even the most dense, inescapable gravitational wells in the cosmos are ultimately dismantled by microscopic quantum fluctuations. This slow death creates a massive problem, known as the information paradox. If a black hole evaporates completely, what happens to the physical data, the exact quantum makeup of everything it ever swallowed? One of the most rigid rules of quantum mechanics dictates that information cannot be destroyed. If a black hole permanently erases the history of the matter inside it when it vanishes, our entire understanding of physics breaks down. To resolve this, theoretical physicists point to the holographic principle. It proposes that the information of objects falling in isn't lost inside, but rather encoded as two-dimensional data directly onto the surface of the event horizon, waiting to be radiated back out. The singularity remains obscured from our view, marking the point where the equations of general relativity and quantum mechanics finally collide and fail. These objects remain the ultimate cosmic laboratories, containing the missing links between the physics of the very large and the very small.